Hello everyone, welcome to the CAC and ME guys. So the strength of material we will cover today. Today we will cover the strain energy. So let's start with the strain energy. What is the strain energy? So basically the strain energy is the energy absorbed by the member or the work done by the load due to the deformation in that member. So we can say that the strain energy is the energy absorbed by a member is called strain energy. Let's take an example. Here is the one block and we are throwing a iron ball on it. Due to the impact, when it will hit to the block, it will absorb the energy which is called the kinetic energy, which is absorbed in terms of the strain energy. Now the strain energy can be further divided into the different type, that is the first one is the resilience. So the resilience is basically the energy absorbed by the member within a elastic region. Within a elastic region is called the resilience. The second one is the proof resilience. The proof resilience is termed as the energy absorbed by the material within an elastic and maximum energy. The maximum energy absorbed by the material within elastic region. It is the, what is the difference between the resilience and proof resilience? It is the energy absorbed by the material within an elastic region. It may be maximum or may not be. But in case of the proof resilience, the maximum energy absorbed by the material within the elastic limit. The third one is the modulus of resilience. So modulus of resilience is given by the proof resilience per unit volume. Modulus of resilience is given by the proof resilience per unit volume, which is equals to the 1 by 2 sigma EL into epsilon up to elastic limit, which can further be written as the stress up to the elastic limit whole square divided by 2E. This is the under elastic deformation. The fourth one is the toughness. The fourth term which is used in the strain energy is called the toughness. The toughness is the energy absorbed by the member just before the fracture point. Energy absorbed by a member just before its fracture point, or we can say that the prior to the fracture. The fifth one is the modulus of toughness. The fifth term which is used in the strain energy is the modulus of toughness. So the modulus of toughness is given by the toughness per unit volume. So it is the area under the strain. So all of these are the area under the stress strain curve and under the impact and modulus of toughness due to the under impact or shock load. It is considered when there is a impact load or shock load or suddenly applied load is there. Suddenly applied load is there, then we will consider the modulus of toughness, which is for the plastic deformation. So let's take how to find all of this values. So here I am taking the stress strain curve. This is the stress strain curve for the mild steel. Here I am taking the stress strain curve for the mild steel, है ना? So this is the straight. This point is proportional limit. This point is called the elastic limit. This point is called the upper yield point. This point is called the lower yield point. This point is termed as the fracture. This point is called a fracture point. So the modulus of resilience. Modulus of the resilience is the area under the stress strain curve up to the elastic limit. And the modulus of toughness is the area under the stress strain curve up to the fracture point under the stress strain curve. So from here we can calculate the value of the toughness or the area under the curve up to the elastic limit is the modulus of resilience, and the area under the stress strain curve up to the fracture point is termed as the toughness. So this area will represent toughness, whether this area represent the modulus of resilience. So from the curve you can understand the clear picture of the modulus of resilience and modulus of toughness. What is the proof resilience? Proof resilience is the strain energy absorbed up to the maximum strain energy up to the elastic limit, and the resilience is the energy absorbed by the material up to the elastic limit. It can be within this point, or this point, or that point, but in case of the proof resilience it will always be up to the maximum to the limit. So it is all about the strain energy and its term. Now we are moving to the how to find the strain energy. So strain energy formula, we will discuss the strain energy formula for the different cases. For the axial load, the strain energy formula for the axial load, for bending moment, and third one is for the twisting moment. For the axial load, the strain energy U is given by the integration of A to B P square xx dx upon 2AE for the xx section. The strain energy for the beam under the pure bending is given by the U is equals to integration of A to B m square xx dx upon 2EI about the neutral axis. And the third one is the twisting moment. In the case of the twisting, The strain energy is given by the integration of A to B T square xx dx upon 2gj for the xx cross section. So for that you can consider that when a cantilever beam take a cross section dx, when axial load P is acting, the bending moment when there is a moment on the bar and twistment due to the twisting, that is the case, a bar which is at the end point a twisting moment T is acting. So all the three cases we have considered. There is another method to find the strain energy of any bar. It is the general formula which is given by the work done method, which is called work done method. The work done method to find the strain energy is given by the work done method to find out the strain energy is given by the U is equals to 1 by 2 P del, and we know that for the axial load the delta is given by the PL by AE. So here we can conclude that it is given by the 1 by 2 P square L upon A. And there are some limitation for the strain energy method by the work done, which is like that. The method cannot be used for the under the uniformly distributed load, uniformly varying load, and when there is more than one load are acting, more than one load is acting. And if the body is under the self weight, the method cannot be used. So when this method can be applied, so let's take an example of the different type. So here I am taking the beam which is under the self weight W, self weight. So this method of the work done by the work done to find the strain energy by the method of the work done cannot be applied if the beam is loaded by the uniformly distributed load. Then method cannot be applied. If the beam is supplied with the multiple loads, then this method cannot be applied. And so when can use this method? So if the beam is, there is a deflection in the beam due to the single load, then this method can be applied. If there is a taper beam of diameter T1 and T2 and there is the axial load acting, then this method also can be applied. So from here we have seen that the different cases of the work done method to find out the strain energy. So when you will apply, first consider this criteria, otherwise it will give the wrong answer. Okay guys, so now the strain energy of now we are moving to the find the strain energy, find the strain energy of prismatic bar under the its self weight. under its self weight. A beam, there is a beam which is having the area A, elasticity, a modulus of elasticity E, and gamma, and the length of the beam is the L. Due to the, here I am taking the cross section, due to the self weight, the reaction will be the R is equals to W equals to gamma AL. So at x equals to 0 to L, the Pxx, the load at the xx section is given by the gamma Ax, or we can say that the Wx by L. And the second one is the area at the section xx, because due to the uniform prismatic bar the area will be the A, and E at the xx is equals to E, because as you know that for the prismatic beam the elastic constant will not change because it is the property of the material. So the strain energy can be written as the integration of 0 to L Wx by L at the section load at the section xx, which is given as the Wx by L to the whole square into dx upon 2aE. On solving this equation, we will find the strain energy of a beam due to the self weight, which is equals to the W square L upon 6aE, or in terms of gamma we can write gamma square AL cube upon 6E. The strain energy of the conical bar, this is for the prismatic beam, and if the beam is the conical bar, then the strain energy derivation we will derive, then we will find the strain energy is equals to the W square L upon 10aE, or in terms of gamma square AL cube upon 6E. And there is one important note for this type of the question. To find the strain energy, it is that the superposition principle cannot be applied, not valid for this type of the question. So if there is a beam and there is a load acting at W at the free end, and there is a movement WL, so we cannot use the superposition theorem to find the strain energy. We cannot use the method of the superposition principle. It is not valid in case of the strain energy. But because as we can see that this W will gives the moment, and this is also giving a moment, so this is the case when the beam acting with the same two or the more load of the same type. But if there are the load of axial load P acting at the free end and there is a moment M, then we can apply the superposition principle, because this load are the different type. So first we will find the strain energy due to the moment, then add with the strain energy due to the axial load. So this method is valid. Okay, add this of 2, which will give total strain energy of beam, which is given here. So moving to, so this is all about the strain energy. What is the strain energy? What are the different type? Which are the formula used? We have discussed all the formula for the axial load and for the bending moment and twisting moment, and we have also discussed the work done energy theorem, and we have discussed the different type of the cases where we can apply this method or not. So this is all about the strain energy overview. So thank you guys, and for more video subscribe our channel. Thank you.